As an engineering team, we are researching to create a device to measure the amount of suspended sediment in rivers. The instrumentation is hanging from a long metal bar above the water. As water flows by the instruments, the resulting drag force makes the bars bend. Our job is to conduct tests on similar metal bars to determine a mathematical model that can be used in the field to determine the optimal instrumentation configuration. Force versus deflection was measured to determine K for each parameter. Then, stiffness versus each parameter was graphed to determine the exponent, which ultimately allowed for the calculations of C for each parameter. This is a graphical example of deflection versus force. There is a linear relationship between them. This is an example of stiffness versus the parameter length as a power function, which determined the exponent parameter of -3, which was then used to determine the constant for the length parameter. After each C was calculated by using the parameters with the exponents previously determined, as well as the calculated K for each case, the mean of the 4 cases was determined and the average C was calculated. The results are displayed in this chart. In order to apply our data and results to a real-life situation, we created our program to calculate either load or deflection, depending on which one the user chose to input. Once prompted, the user entered the thickness, length, and width, as well as the load or deflection, and the opposite was calculated. We were able to calculate the actual deflection and load mass based upon our MATLAB program and compare it to our predicted values, as well as calculating the percent error. The third part of our project was to design a cantilever beam for a wastewater treatment facility in El Salvador for Engineers Without Borders. This picture shows a diagram of the setup for the system. Here is a list of the requirements for our optimal beam configuration. Only have one of each beam available. Up to 3 instruments that cause drag can be used on each beam. All 3 instruments can be used in the same location on a beam with the use of mounting brackets. The cantilever beam must be submerged at least 6 inches underwater and have at least 12 inches of beam above water. Beams are clamped at the top of the support frame without any of the beam length extending above the top of the frame, and there can be no more than 1 inch deflection. Provided a chart of available beams with specified cross-sections, lengths, and costs, we used our MATLAB program to determine the maximum load per beam by choosing to enter a deflection of 1 inch when prompted. This Excel chart displays the ideal beams to be used for the design. By analyzing our Excel data that was calculated with MATLAB, the optimal beam configuration can be determined. Our first beam would be made of stainless steel with a width and thickness of 1/4 inch, with a length of 18 inches, and would ultimately cost $10. The instruments on the bottom would be a portable sampler and a pH electrode. Beam 2 would be made out of aluminum with a width of 1/4 of an inch and a thickness of 1/2 inch and a length of 18 inches, with also a cost of $10. Instruments on the end would include the turbidity meter, velocity flow meter, and nutrient meter. Based off the data collected, it can be determined that by switching the orientation of the width and length of a beam, a higher load force can be reached because thickness has an exponential relationship to stiffness. It is to the 3rd power when it is increased versus width, which is a linear relationship as it increases. The total drag of instruments, 10.5 pounds force, needed to be distributed between 2 beams that could withstand the force with less than 1 inch of deflection in the water. Overall, by looking at the cost and the load of each beam can handle, the most cost was determined, and it was a cost of $20.